Vadusevan and thanks, Prashant.
I should say I did not anticipate an entire day's preface to my talk. Yeah, hi. So I'm going to talk to you about some work joined with me, Chetan, Omar, and Ron, which is titled Batch Proofs of Statistically Hiding, which is perhaps the main message to take away from what I'm going to say. And there are a couple of different ways of viewing what I'm going to tell you. And the perspective I'm going to take today is that we provide answers to this question, the question of when can you batch proofs. So let me start by defining my terms, because I'm going to use them in a slightly different way from what we had earlier. For batch proof, to me, for an NP language L, looks like this. You have a prover and a verifier, and you have T instances. Both of them know this. The prover knows witnesses for these instances, if there is instances. And they talk, and the prover is trying to prove to the verifier that all of the instances are in the language. And the essential properties I care about are it has to be complete, and everything is going to be perfectly complete. Don't think about that. I want both these parties to be polynomial time. The prover polynomial time given the witnesses. I want the proof system to be succinct, meaning that the total communication in the entire system is much less than T. Let's say T to the 1 minus epsilon for some constant epsilon. And the system is statistically smooth. This is a batch proof. And if it helps, you can think of this T as being significantly larger than the instances in the witnesses. So some tricky issues don't come up. Very basic primitive, a very basic complexity theoretic object. You have T instances, T witnesses. Can I prove to you that all of them are in the language without having to communicate all my witnesses to you? Right? And I'm going to ask a very fundamental question about this fundamental primitive, which is which languages in NP can have these proof systems? Surprisingly, we do not have that many good answers to this question. We know, sure, yeah, all P. Yeah. Is there anything interesting beside that? And yeah, surprisingly, we don't have that many interesting answers to this question outside P. We know, due to a few papers by Ron, Guy, and Omar, that you can do these for languages in UP.
How many of these are roast groups?
So I have a better joke than this, but this is not the audience. Yeah, so we know this. And you can probably get these for some specific structured languages even outside UP. I don't know any simple languages that have this property, but I can tell you more about this later if you're interested. And this is basically everything we know. You know that you can do this for this, and that's all we know. And so, yeah, the world sort of looks like this. You have, you can do it for P, UP, and some other languages here and there. We don't know anything else. And what I want to ask is, what else can you get this for? In particular, can you get it for all of NP? Right? Can you get it for SAT? Can you get this for SAT? And how many people think we should be able to get this for SAT?
No, statistical. Statistical.
Nothing. Yeah, not assuming anything.
Of course you should be able to do it. What, seriously? Nobody raises their hands?
I don't know. Okay, I have 7 people, 8 people.
I want the same amount that you paid her.
Can I ask a question before that?
Yes.
It's promotable. So what if you don't do UP, you do something like UP, you have a unique answer. What happens if you have a small number of options?
Yeah, you can do things.
No, where does it stop? No, where does it stop?
Even with 2 it stops.
UP.
Oh, you can't?
UP.
Even 2 it
Okay, so you could, but okay, apparently you cannot. We don't know.
Yeah.
So what's the answer to my question?
No, we cannot.
We don't know how to do it.
We don't know.
So we don't know.
Yeah, we don't know.
So this is really all we know. I thought we knew more.
Just ask Prashant.
Yeah.
It's just two. I don't remember. Some sessions there were topics.
All right, this is all we know. Right? And what I want to say, one of the things that you're able to say is we will make you some. So for the record, I think you should not be able to do this. and what we give is some sort of justification for why you should not be, or at least some way to bolster my position on this question. Right? We show something like this. We show that if a language has batch proofs, then it has a certain kind of statistically witnessable distribution. Right? And let me again define all this so we are on the same page. What is witness indistinguishability? Well, so you have take any instance in the language and two different witnesses for it. And imagine running a proof system you have with both these instances, both these witnesses. And what we want is that these executions look the same to the verifier. Even if the verifier is trying to actively figure out which witness you used, you cannot take. Yeah, for any malicious, possibly malicious verifier, you can't tell. Statistically, you cannot. The views of the verifier in the two executions are statistical views, right? And to some error, to some small. Yeah, an honest verifier is doing the same thing only for honest verifiers. One thing to point out is that if we have inefficient provers as a studio, so this is a thing that only really is only meaningful if you have efficient provers, which is what I'm talking about. So with this, let me tell you more precisely what we are able to show. So we show that if you have a batch proof for a language, then you have an honest verifier as a proof for it, with a couple of caveats. This proof has a non-uniform prover, and its error, witness indistinguishability error, is 1 over polynomial, as opposed to exponentially small, negligibly small. And I want to say that if you think of this as a construction, if you think of this as a way of constructing these proofs, then these are perhaps things that are of concern to you. But if the perspective you're taking is what I want to take here, and think of these as indications of whether these proofs exist or not. And I want to suggest that these differences are not, these caveats are not magical.
What is the dependence on the successiveness for the? I'll tell you.
Can you clarify what this error means? Like this is a 140.
It's the distance between the views of the verified in the two cases.
So like again, you want it to be ideally to be negligible, so you get to be small.
Yeah. And total variation distance.
So how far away do you have to go for an emission factor for else? Such that you can actually prove that it does exist, like for NP?
Second, how far?
Like, so there's this definition, which is batch proof, let's say for that. How far do you have to modify the definition before you can rule it out?
How much stronger do you have to make batch proofs before you can do that? Well, if you're only communicating a very small number of bits, a constant number of bits,
Below what the one witness is it causes
yeah.
kind of hierarchies to collapse into.
I see.
Below one witness, at least you can certainly see that some exponential thing hypothesis will prove that out, but you're saying there's even more evidence.
No. Varies like the complexity.
So
One should say that you can get batch proofs for NP with a P space on a
Yeah,
scooper.
Yes.
So anything so it's a little, how do you rule it out? Like, it's just a question of the efficiency of the prover. So this is one way of showing implication.
Yeah, let me repeat that just to point it out that if I did not have the restriction of the prover being efficient, then you can't get this for anything in NP simply because of P equals P space. You go to P space algorithm and come back to it. But with efficient provers,
I expect to preserve rounds.
yes. Let's take one more round.
Does the non-uniform advice depend on the X, the statement you're proving?
No, then it's trivial.
Okay. So this is interesting, even if there's just two witnesses, right? So you that says that you don't expect batch proofs even for language. That's two witnesses. This is interesting, even if there's just two witnesses, right? So that you don't expect batch proofs even for two witnesses, right?
Yeah. If you believe you don't have witness.
Sorry, you're right, because they were requiring T to the 1 minus epsilon. They were requiring not even one bit for each of these.
Yeah, that's why it's very So I can show this and if you carry it,
Sorry, I have a question. Why do we not expect statistical W1? Just because we don't know. Like, is there a reason? Is there any reason beyond the fact that we have no idea how to do it?
I'll get done.
Okay.
Answers, I don't have a good reason, but I say we.
So like statistical zero knowledge, you don't expect
Yeah,
unconditionally.
but statistical W1 is a different story.
But think of a language like some disjunction language, which like one that says One is an elephant and one is a giraffe.
Yeah.
And they're mapped, two totally different witnesses are going to be mapped efficiently to the same kind of communication. It sounds really weird, but
Yeah, that is basically my reason for feeling that they should not exist. But then, more surprising things have happened in my lifetime.
So we don't expect like SWI to be close under complement, I guess.
Yeah, because it contains UP, for example. So we don't really expect that. I'll say a bit more about this stuff in a minute, but we just finish up here by saying that if you really care, you can actually make these malicious verifiers with the proofs in certain cases or with certain assumptions. But again, if you may care about this if you care about it as a construction, but I want to say that for my purpose, that's good enough. And now
Is the one you get public
so if you start with a public coin batch proof, you get a public coin. This is uneven going. Always it won't be.
Are there languages where we have this SWI but not that proof?
I say a little bit about it.
Yeah, good. So why do people here say that this SWI is so different than zero knowledge? I mean, so that's why
You can think of SWA sort of as zero knowledge, but with an unbounded similarity.
right, of course, but why can't you do the FLS thing of doing zero knowledge using WI?
You need some assumptions.
Yeah. So yeah.
But you want to be able to statistically hiding and statistical example.
Also, yeah.
Okay, maybe.
If we're talking about arguments, then that would be more relevant. So this, and in other words, if you believe that your language does not have these proofs, then it does not have that. I don't know. Now, to answer the question we were asking earlier, we can ask this question: which languages have SWA proofs? Certainly, P does, and you can see that UP does, vacuously does, because every instance has one witness, right? And perhaps this is sort of an explanation for why UP was the class for which we first found batch proofs, because it's trivially satisfies.
What's the soundness of the SWI proof?
Statistical.
Oh,
There's normal. Statistical.
negligible.
Yeah, that's it. You can also show that languages in this class have SWA proofs. Because it's a zero knowledge proof, and the only remaining question is, do you have an efficient proof for these things? And we know, due to some very interesting work that these languages do have zero knowledge proofs with efficient proofs. So you also have SWA. And these classes in this languages in this class are maybe an example for languages that are not in UP that have SWA proofs. For which we can take some combinations of these languages, and of language from here, language from that. But now we can ask. So how many people think that SAT has?
Yeah. I would be surprised. I mean, I don't think it's like a thing we should be scared of. I'm on the fence.
We were asking in the beginning, how many people believe that there is SWI for all the P? Maybe it's not really increased.
Yeah, I should have done that. Yeah, that's the experiment I should have. So 2.5. And so
Counts as 1.5.
So 3 or 4. And now this is the number of people who believe that NP has batch proofs. So I have already delivered something in my talk. Yeah, so this is. Yeah.
Can you go slightly beyond SDK, no, and for or whatever?
Yeah. So these are all good questions. Towards answering this question, the guy was saying earlier, you don't expect SAT to have SDK proofs because with all this hierarchical office. It's not clear how to show that for SWA because SWA is I wouldn't think it's incoherent. It contains UP. It's probably not going to be incoherent. So you probably can't go in the same direction to show that NP having SWA proofs is going to cause some catastrophe. So it's my belief in this is not as strong as all my hierarchy stuff, but yeah, this is how much we know.
Can you repeat that last part again?
So I was saying my faith that NP does not have these proofs is clearly not as strong as my faith that NP does not have SDK proofs, because it doesn't have catastrophic consequences. At least so far, as far as we can tell, it does not have catastrophic consequences. And that's a very interesting question to try to answer. Would there be catastrophic consequences if NP does not?
Are there implications from witness hiding?
Not. So witness hiding is more of a computational notion. So wouldn't really play a role here.
Does the picture change if you ask about non-interactive SWI?
In these respects, maybe I don't know. I don't know how. I don't have any conclusive things to say about that. But maybe I'll say a little bit later. Okay. So all this for proofs. So maybe you don't have proofs for NP, batch proof for NP, right? But what we know we do have is arguments. You relax your soundness to be computational, and we know how to construct batch arguments for NP from a bunch of different. And I'm talking about interactive batch arguments, non-interactive data, interactive batch arguments, and we know how to construct these. And the relevant question here is what assumptions you need, or what assumptions are sufficient to construct these. And we've known for a long time that you can use Gaussian listening hash functions to get even constant round batch functions. Something even you can get constant round succinct proofs arguments for NP, right? So in particular batch arguments. Recently, people noticed that you can actually improve this to something slightly weaker, seemingly weaker at least, which are these multi-collision listening hash functions. And these seem to be the weakest assumptions in order to construct this. And the question I want to ask here is what assumptions are necessary? What really is the weaker? What is the real complexity of this problem? What assumptions do we need to construct batch arguments for all of it? And over here also we can say something, we can draw some similar conclusions from batch arguments. It's the same approach. We can show that if you have batch arguments for all of NP, this is not language specific this time. If you have it for all of NP, then you end up with these similar HV arguments for all of NP. And this is also round preserving. Here we care about it a bit more because constant rounds in the limit. And it has the same caveats as before. And further, with if you assume a little bit more, if you assume one-way functions, then you can use some somewhat standard transformations to actually get SDK arguments with about the same number of rounds. It's the same caveats, but about the same number of rounds. And so in a sense, this sort of ties together the complexity of batch arguments and SDK arguments. Like whatever you believe about SDK, whatever you believe you need for SDK arguments, you can propagate.
We have this last.
Yeah. You have this from one of them?
Actually.
Yeah. Think of response.
Oh, okay.
For if R is polynomial, then you do functions, and there you don't really. That this line of inference doesn't really tell you anything about it. So where this does what tell you something is about constant numbers. So interpreting that for R being a constant, you have this. You have constant on batch arguments for NP, and you assume one function, then you have constant on SDK. And this is something you only know from statistically hidden companies. So to paraphrase this again, if one-way functions could give you constant on batch arguments for NP, then they would also give you constant on SDK arguments. And so whatever you believe about this, now we also believe about this. Yeah, this is the answer I promised Guy the other day.
Not an answer to the question, but maybe it was. What was the question about? It wasn't about batching. Are you saying that the batch should be some?
You're asking about succinct arguments.
So we're going past P to Bargland or to NP. Oh, you're saying a succinct argument for NP is even stronger.
Yeah.
So you're saying that with a constant number of rounds.
But even if it's super concentrated for to get it's happening from a function for no number of times in a security. Sure.
So this, any other comments or questions? And so, so let me tell you very quickly what we have for the non-interactive case, and then I'll like to spend some time telling you how we get this, because I find it very interesting. So yeah, non-interactive batch arguments, not going to tell you too much. It's non-interactive, you have a CRS that comes from somewhere. And typically you ask for adaptive soundness for these things. And there we can show something again very simple. And we know a number of constructions now from specific assumptions. Right? And here also I want to ask the same question. What assumptions are actually necessary for these things? And we can show something very similar. Right? That you can take a batch argument and get a residual argument, same values. And you can also show that by some connections through PAR, you can get lossy PKE from these. And you can put these together to get, again, non-interactive residual arguments for all anything. But we are also able to amplify it using the lossy PKE to get actual negligible. So that's all I want to say about this, unless someone has. So these are all the results that I want to tell you about. I'm going to move on to telling you how we get things. You can take a minute, tell me if you have any questions or comments.
So in the interactive setting, like the 2 slides ago, you cannot get a negligible soundness error.
Yeah, that is one thing we don't know how to do.
Oh, I mean, why doesn't parallel?
Did you say soundness or
The oh yeah, sorry, it's
soundness? Yeah.
simulation error. Okay.
But what's this result about lossy PKE? Because don't we have non-interactive batch arguments from like heuristic from hash functions things that don't imply PKE, like the achievers? Seems surprising that batch arguments would imply.
No, this is like a strong, under strong soundness.
Oh yeah. So I haven't told you what soundness I am using here.
Oh, okay.
What I need is some English. I need some more extractive soundness.
Okay, I see.
I just want to clarify. I think Marshall asked this question. So it's still a little bit whether there's a non-interactive statistical witness indistinguishable from SAT. Is that true?
If you're talking about proofs, yeah, even interactive, I don't know.
Yeah.
It's not to imply anything.
Yeah. Oh, yeah. It's not to imply anything. Yeah. Is that the answer?
Yeah.
I don't know. I mean,
Organization and defining canonical witness, right?
yeah, it's like a distributional canonical witness. That's a good way to think of non-interactive distribution. That you have these different witnesses, and from any of them, you are able to sample the same distribution. It's just something very odd.
So it might be a slightly different problem, right? Might be a witness for a related problem.
Okay, so let's move on. I'll tell you.
Just this question, just finding even one witness, different witness. Like I'm trying to find this non-distribution version. What do we know about this?
Yeah, that would be something even stronger.
Yeah.
Can we rule that out, for example?
Yeah.
I give you SAT formula, I give you one satisfying assessment, can you find another?
No, but you know that you cannot do that.
Always add a trivial witness.
Yeah,
You know.
Oh. Then just non-interactive.
Smaller witness.
Or even let's say I want
Like
you
smaller
to
witness.
something that is not directly in the line of implications, but what if I give you a random witness and I want you to find another witness? Maybe you can also do that one by these things, but all questions, things to understand.
What are you saying?
No, this doesn't make sense.
Okay. Something in which trivial thing of planting doesn't work.
Yeah.
Anything like that.
Okay, so let me tell you how we do this. And let's I'm going to show you what we do in the simplest case. Possible. Take a language that has a batch NP2, meaning the prover just computes, the prover has all these witnesses. There is some proof computing function f that the prover uses to compute the proof. It sends the proof over, and the guarantee you have is that the verifier accepts this proof if and only if all the instances of the language. And yeah, everyone is polynomial time.
Are you in the non-interactive setting now?
Proofs.
Is in the proof lab.
Yeah.
Statistical soundness, but for simplicity, think of an interactive.
Yeah, I'm going to show you what we do here, and I'm going to tell you how to extend this.
To the interactive setting. So everything you're saying actually works in the interactive setting. Okay.
Yeah, we need to make one small change, but okay. Isn't all the ideas are here. Yeah, so take the simplest possible case where everyone is deterministic. Everyone is polynomial time, everyone is deterministic. Right? And this is what the proof system looks like. And I also tell you the size of the proof is much less than t. Right? Simplest thing, can you show that this language L has some stability? And the approach we take is very close to this this approach that is in retrospect quite simple and natural, but very clever approach taken by Andrew Drucker in the context of instance compression. And if I have time, I'll tell you about this at the end of the talk. It's very cool. Yeah, so we want this. And what are we going to do? Yeah, what should we do? So I have this, right? I want to come up with a SWA proof for N. So in that proof, I'm going to be given one instance and one witness. How am I going to use this to do anything with that? It's one way. Any other ideas?
Pick others.
That's sort of what I'm going to do. So, and the intuition underlying everything I'm going to do is the fact that this proof is shrinking, right? So, and in particular, it has fewer bits than the number of witnesses that the proof was given. So it cannot possibly remember all of the witnesses. It cannot possibly remember even one bit from every witness. Now, what I'm hoping to do is to take the witness I am given for the one specific instance and put it somewhere and hope that the proof pi forgets about it. So that's what I'm going to do. So at a high level, this is the approach. I'm going to, given this X and the prover has a W, the prover is somehow going to pick a number of other instance witness pairs in the language. I have to figure out how to do that. It's going to do that. And it's going to pick a random location among the t locations, put the specific instance witness pair there, and whatever it sampled over here everywhere else. Okay. And it's going to compute the proof that comes out of this. And it's going to send over to the verifier this proof and also all the instances that it came up with.
What is F again?
F is the function that computes the proof in the batch NP. So going to do this. And what the verifier does is also is quite simple. It runs the batch verifier with this instance. So it takes all the x's that the prover told it. It's going to put it appropriately. It's going to insert the x in the jth position. And it's going to use the batch proof pi and going to see whether it verifies. I want to claim
that just convinces us that there is statistical WI proofs.
Thank you. Thanks for coming to this talk.
Right.
Yeah.
It's like a lot of the works in the literature like have one particular witness that is like completely remembered, and the prover can't find out what it is. So
yeah, so this is the challenge. Right? So I hope it's clear that the system is complete and sound. That part is fine. But why is it WI? I want to show you that there is some way in which you can pick these XIWI that makes this Windows distribution. Right? And it's not obvious, but we're going to do it. Yeah, so this is the view of the verifier that we're going to read about. Come back later. And the big question is the fitness distinguishable? So let's take the simplest case, okay? Let's say that there is some one instance and two of its witnesses that we care about. Forget about everything else. I only want my proof system to be witness indistinguishable for this instance and these two witnesses. Let's say I want to do this. And now, is there a way to pick the Xi's and Wi's so that this happens, so that the proof system is witness indistinguishable for this instance and these witnesses?
You're sampling more witnesses. Like, how do you get those XIs, WIs in the first place?
That's why the proof is going to
That's
come.
advice.
Yeah.
It's going to come as a non-uniform advice.
But you're saying that proof system may be
geared toward this particular instance?
Or
I mean, just to make it hard, your life hard. Because the pi may always, it looks for x. If x is there, it puts w.
Yeah, that's what I'm really worried about. And that's the kind of thing that's perhaps simplest adversary that could break witness indistinguishability, which is where it looks for one specific instance x. If it finds that, it just outputs the w. And because the output length of this f is smaller than t, but it's still larger than one witness, it can still output a few of the witnesses. Right. That's what I'm worried about. That's what I want to know. And now I want to say that if you only care about witness indistinguishability for one specific instance and two specific witnesses, then there is a way to avoid this specific attack. The f that looks for this x and outputs the witness that comes with it. What is that? How do you do that? Yeah. So that's what I'm going to do. What I'm going to do is I'm going to pick all of my xi's to be the same x, and each of my wi's I'm going to pick at random from the two instances that I care about. And so the attacker that looks for the x and outputs the witness that comes with it now has no idea which witness I used, because all the instances are x, and I've used both the witnesses.
Actually, as you describe it, there's a polynomial advantage.
There is a polynomial advantage. All right, so this is simple. And how am I going to prove that this is fine? So at least for this particular attacker, this particular adversarial f, this works. You can have more general f, and it turns out you can actually show that this is good enough for any adversarial f. And the way you do this is using this, this very clean and simple lemma about compressing functions from Drucker and simplified consequently by Dell, which is this, okay? Take any function, g, that is shrinking by even some constant factor, and look at the following two distributions. So the first distribution is I pick a random j, and that j I fix to be 0. All the other inputs are random. And the other distribution is again I pick a random j, and that particular jth entry I fix to be 1, and everything else is random. So these are two distributions, and what you can show using some elementary information theoretic arguments is that these two are statistically close. And what this is and so what this is a statement about essentially the noise sensitivity of shrinking functions. It's saying that if you have a function that shrinks, then it cannot really depend that heavily on every single bit. It probably doesn't depend that much on some of the bits.
Isn't something similar tell in your paper on VIR?
I take one OT from VIR in like 1998.
Okay, I will do this because that would read it.
It's like a clean formulation.
I'm sure we already did it in 98.
I don't follow because these came much later. These are like 10 years ago. It's a simple lemma, right? And this dependence is also tight. This on square root is wrong, and that's I leave that as homework for you to figure out that. Sure. Right. So simple lemma, and it turns out to be exactly what we want, right? Because what we're doing is exactly this, right? We are fixing either W0 or W1 in our proof, and I'll tell you more. So let's go over what we did so far. So if we fix some x W0 W1 for which you want W1, and you set every xi to be x, every wi to be a random one of these, you pick the random location, and you put the witness you care about in the location, and the other things in the other places, and you got this proof. Right? We put W0, it's pi 0, W1 is pi 1. And all you have to do is apply the lemma I just showed you with this function g. The function that takes these input bits and uses the bits to select which witness goes there. And you immediately get what you want. You immediately get that these two are successfully close. Right? And it turns out you can actually extend this quite easily to distributions as well. Like so far, I fixed one instance on a pair of instances. But let's say you had some distribution over an instance in terms of witnesses that you wanted to get W over. So I have this proof system, and I care only about witness indistinguishability for instance witnesses drawn from this distribution. And you can do exactly the same thing. Like this is what I care about WI for. And you do exactly the same thing. You sample all the Xi's and Wi's also from this distribution, put it there. And again, this will fool the adversarial function. It won't know which is the actual instance and which were actually also which ones were just sampled from the same distribution. And you can apply the lemma again, and you can get something very similar.
Wait,
But this recursive.
no, but what, I mean, there can be. It's not the same X every time? Different X's here?
Yeah.
So why can't the compression function remember one X and one witness, and if that is the X and the witness? Like, this is a high probability statement over the random X. It won't work for everyone.
This is a statement only in expectation. It does not work over every X.
But this requires like the prover to know both W0 and W1, right?
It requires the prover to be able to sample from this distribution.
Well, it's not a statement for every, it's just a statement for random sample.
Yeah.
Yes, but the prover doesn't, normally a prover just gets like a single X and W and has to prove, like can sample from the distribution, that's fine. But that's not what,
So
you
what
need to know both W0 and W1.
Actually, no, because what the prover is doing is for all the instance witness it is given, it is putting it there as is. The other locations are sampled in this way.
But then he has to sample WI condition on X, right? That if he only gets one of them.
No, so the thing is, all these X's will not be the same.
Oh, these are different.
Yeah.
Sorry,
You sample
I missed
them
this.
afresh from the
I
distribution.
missed this, okay, good.
Oh, sorry. So you're still sampling X from D. You're not preparing D after seeing X.
No. Yeah, the order in which things happen is someone in the sky samples this and gives me just one of the two. I'm the prover. Someone in the sky is sampling this, giving me one of the two witnesses. I am sampling these things, and I am sampling these, I'm sampling this, and computing this. So for the specific instance that you care about, you only know one witness, but for the others, you know one. So,
don't really need to have two witnesses. You just need to have something about the distribution of the witness within the instance, right?
Yeah. It's a simpler 5 minutes. Okay. Yeah. So we have this, and this is this kind of distributional notion of witness and distribution, right? Because you only have the guarantee in expectation over this distribution, this specific distribution. But the nice thing is you have this for every distribution. In particular, what you have is this. You have a proof system that, or rather, for every distribution over the X W1, there is some distribution from which you can sample the X's and W's, for which the proof system is WI for that distribution. Right, so you have this kind of distributional WI. What you really want, however, is you want actual WI. You want something that works for every instance. Right? In particular, you want a way to sample the X's and Wi's that is separate from the X, ideally separate from the X, but you want that to be one way to pick all the X's and Wi's that works for every possible instance in class of indices. So what am I going to do?
Min-max.
I do min-max, and now I'm not going to go into details because I don't have much time, but left as homework. You can do min-max, and I still want to be able to sample this. Min-max doesn't give you samplability, but you can do in sparse versions of min-max, which is where the non-uniformity comes from. Because what you really do is you take many samples from this, and then you sample from the empirical distribution. Yeah, this is the entire proof. It's not that hard to fill in the details. You can handle more rounds. Any questions?
So the error is the compression lemma error and min-max.
Yeah. No, sorry. Yeah, you can handle more rounds by just flattening the protocol, because when you're talking about WI, you only care about the honest prover. So you can imagine the verifier actually sends its randomness to the prover.
Honest verifier.
Honest verifier and honest prover. So you can sort of flatten the protocol and prove it for that. You can figure it out. And yeah, this is all the technical stuff I wanted to tell you. And I have a bunch of questions that come out of this. A lot of things I don't know. I would like to know. Starting with this, the question is started out with, can you actually get batch proofs for NP? And to answer that, you have to ask, can you get SWA for NP? But more generally, there are lots of properties about SWA we do not know, that we do not know whether it has or not. Which is again in contrast to this class SEK, for which we know a lot of things. Right? And really the big difference in our ability to analyze these classes is that SDK has this efficiency simulator. You can do a lot of things with efficiency simulator, but SDK does not. It seems to make it quite different. I would like to understand, is it closed under different operations? What does it have? Another really interesting question is whether you can make the proof uniform in that construction. The non-uniformity came from this min-max. Can you make it uniform? You could try applying the uniform min-max theorems that we know, but those have our games don't have the properties you need for them to work. I'll tell you more later. And also, another property I don't know about SWA is whether you can amplify the error. Whether if you start with inverse polynomial, can you get it negligible? Independent question. There are other questions. Can you show stronger bounds for, let's say, non-interactive batch proofs, right? Which should be even less powerful. And in particular, the batch proofs we know for UP are interactive. They take, I think they work for any constant number of rounds. And the trade-off in the communication is such that if you try to do this kind of round detection for these interactive proofs, you end up with something trivial if you try to make them non-interactive or even like two message. So is that inherent? Is it that non-interactive batch proofs are significantly weaker than, significantly stronger than actual batch proofs and more limited? And in that case, it's not even clear that unbounded provers can do much. Here for a constant number of rounds, actually, the IB piece-based connection still requires like a polynomial number of rounds. So constant non-batch proofs, you can still ask, even if with unbounded prover, what can I do? Not clear. Yeah, can you, rather than act as constructions, can you get constructions for the languages? Do you guys have any other questions to ask?
Yes. So I think it's super interesting to get batch proofs for NP, where the communication can grow, say, linearly with a number of instances, but you're not sending T witnesses. You're sending one witness plus T times something.
Yeah. So I think this approach might work for a small extent, maybe till like T log n bits or something. This could still work, but beyond that.
Can you give any non-trivial upper bound of SWI under the B space or something like that?
Oh, well, it only makes sense for languages in NP. For witnesses, it's defined. I don't know any other beyond NP. I don't know any. I don't know what it is.
Upper bound, I know. Well, would SWI live like?
I don't know. It could even be NP. We don't know that it cannot be NP. We don't have very strong reasons to believe it cannot be all of NP. And I really like to understand.
The other level is statistical, the wonderful phenomenon. Like for SDK, if you allow such error in the statistical distance, it is still limited.
For SDK, you can amplify that. But with the efficient prover, actually, I think you can still do it while preserving efficiency. I'm not sure.
Okay,
Yeah.
we can take further questions. The same question. I'm sure.
Which would be nice. Oh, wait, but if I start the presentation already.
Okay, great. So up to now, we've been talking about the computational assumptions. Now Tal will tell us a bit about physical assumptions and how they interact with computational with complexity assumptions. So,
Yes, thank you. Hi,